back to my channel BFD, Fake Passion Behind the Movie and the Dance Show. Today's topic is mechanical properties of fluids. Substances that can flow are called fluids. It has no definite shape of its own and offers very little resistance to the shear stress. The shearing stress of fluid is about millions times smaller than that of solid. The study of fluid at rest is known as hydrostatics. Average pressure. It is defined as the normal force acting per unit area. P average equals to F by A or delta F by delta A for finite value, where F is the normal force acting on the area. Pressure. The limiting value of average pressure is called pressure. It is denoted by P. That is P equals to limit delta F by delta A. Delta A tends to 0 equals to dF by dA. It is a scalar quantity and unit Newton per meter square, which is called Pascal. And dimensional formula is given by m into L into T to the power minus 2 by L to the power 2 equals to m into L minus 1 T to the L to the power minus 1 and T to the power minus 2. Atmospheric pressure 1 atm. It is the pressure exerted by atmosphere at sea level. Its value is 1.013 into 10 to the power 5 Pascal or 1.03 into 10 to the power 5 Newton per meter square. This is the value of 1 atmospheric pressure, that is ATM. Density. It is defined as the mass per unit volume. It is denoted by rho. That is rho equals to m by v, given mass and the volume occupied by the given mass, divided by volume occupied by the given mass. Unit kilogram per meter cube. Dimensional formula m into L to the power minus 3. Now density of water at 4 degrees Celsius, rho W is equal to 1.0 into 10 to the power 3 kg per meter cube. Relative density RD of a substance. Relative density of a substance, that is RD of a substance. It is the ratio of density of a substance to the density of a water at 4 degrees Celsius. Hence, RD equals to rho water by rho substance by rho water. Example, for example, RD of iron equals to rho iron by rho water. Thus, it is a number and dimensionless and unitless. RD of aluminium 2.7. Then we can calculate the density of aluminium from above formula. Hence, density of aluminium will be 2.7 into density of water, which is 1 into 10 to the power 3. So, 2.7 into 1 into 10 to the power 3 kg per meter cube. It shows that if the RD of a substance or material is given, then we can calculate the density of that substance by above formula. Pascal's law. The pressure in a fluid at rest is the same at all points if they are at the same height. This is the Pascal's law. Here the proof of Pascal's law is given. Let the effect of gravity is neglected because considered prismatic element is very small, and so every part of it can be considered at the same depth from the liquid surface or from the same height from the bottom surface. In the figure, force on face ACFD ACFT is FB. Force on the face ABED equals to FC, and force on the face BCFE equals to FA. Area of face ACFD equals to AB. Area of face ABED equals to AC, and area of face BCEF equals to AA. Now for the equilibrium, FB sin theta 2 equals to FC, and FB cos theta equals to FA as shown in the figure. From geometry, AC equals to AB sin theta 2. Hence, sin theta equals to AC by AB, equation 3, and AA equals to AB cos theta 2, or cos theta equals to AA by AB, equation 4. From 1 and 3, FC by FB equals to AC by AB. This implies FC by AC equals to FB by AB. This implies PC equals to PB. And from 2 and 4, FA by FB equals to AA by AB. This implies FA by AA equals to FB by AB. This implies PA equals to PB. Hence PA equals to PB equals to PC. Hence pressure exerted at point is same in all direction in a fluid at the rest. Proved. Now variation of pressure with depth. Consider a cylindrical element of fluid of base area A and height h in the container containing liquid of density rho. Let the pressure at surface 1 as shown in the figure, which is of what phase. At surface 1 and 2 is P1 and P2. 1 is the upward surface and 2 is the bottom surface of considered cylindrical element. Since the fluid element is at rest, so horizontal and vertical force on the element must be 0. Now for vertical equilibrium, this force must be equals to F1 plus mg must equals to F2. So F1 plus mg equals to F2, where m is the mass of element, or F1 can be written as P1 into A plus mass is V into rho, that is volume and density of the given element, into G, or equals to P2A, where rho is the density of liquid. Now we have volume V equals to height into base area, or area cross-sectional area, equals to volume of the element. Hence P1 into A plus HA into rho G equals to P2 into A. This implies P1 plus H rho G equals to P2. Hence P2 minus P1 equals to H rho G. This is the expression for pressure difference between 2 points separated by height h inside the fluid. Now if surface 1 is at free surface of liquid, then P1 equals to PA equals to atmospheric pressure, and taking P2 as P, equation 1 becomes P minus PA equals to H rho G, or P equals to PA plus H rho G. Equation second. This is the expression for pressure at a point H below the fluid surface. This pressure is called hydrostatic pressure or absolute pressure. That is, we can say that the pressure below at height h from the free surface is equal to P equals to PA plus H rho G, where PA is the atmospheric pressure, H is the height below the free surface, rho is the liquid density of the liquid, and G is the acceleration due to gravity. Now gauge pressure. The difference between hydrostatic pressure and atmospheric pressure is called gauge pressure. Hence gauge pressure equals to P minus PA equals to H rho G. where h is equal to depth of the point from free surface. Atmospheric pressure. The pressure of the atmosphere at any point is equal to the weight of a column of air of unit cross-sectional area extended from that point to the top of the atmosphere. At sea level, its value is 1.013 into 10 to the power 5 Pascal, or equals to 1.013 into 10 to the power 5 Newton per meter square, or 1 atm. Yeah, 1 atmospheric pressure equals to 1.013 into 10 to the power 5 Pascal. Barometer. It is a device used to measure atmospheric pressure. It consists of a glass tube closed at one end and filled with mercury inverted into a trough of mercury as shown in the figure. The space above the mercury column in the tube contains only mercury vapor, whose pressure P is so small that it may be neglected. The pressure inside the column at point A must be equal to the pressure at point B, which is at the same level. Because point A and B is at same level, so pressure at A must be equal to pressure at B. Hence, PV equals to PA. Now we know that this implies PV equals to H rho G equals to atmospheric pressure. For this condition, a pressure at A will be given as H rho G. So, and PV equals to PA. So we have written PV equals to H rho G, and this will be the equal to the atmospheric pressure. Hence, PA equals to H rho G. Now H equal to 760 cm, 0.76 meter, and rho equal to 13.6 gram per cc for mercury, equal to 3.6 into 10 to the power 3 kg per meter cube, and G equals to 9.81 meter per second square. Putting these values, we get atmospheric pressure PA equals to, solving, we get 1.013 into 10 to the power 5 Pascal, which is equals to 1 atmospheric pressure. Another unit of pressure, 1 millimeter of Hg equals to 1 torr, which is equals to 133 Pascal, and 1 bar equals to 10 to the power 5 Pascal. These are another units generally used practically. Manometer. It is a device used to measure the pressure of gas inside a container. Let's see the figure as shown in the figure. PA, pressure of gas at this point. Consider 2 point A and B as shown in the figure, and this is the free surface. Since A and B are in the same level, so pressure must be equal. Hence PA equals to PB equals to PA plus rho Gs. From this formula, here will be pressure of atmospheric pressure, and this point is at depth H. So pressure at this point will be atmospheric pressure plus H rho G. So this is written PA plus rho GH. And this will be equal to the pressure applied by this gas, because both are in same level. Pascal's law for transmission of fluid pressure. Whenever external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. Here situation is shown in the figure. Here a piston is connected in the cylindrical limb. If we apply a force F and a pressure is generated delta P at this point, then this pressure will be transmitted all over the fluid, from that is at B, at C, at the this valve, at this valve, at this valve, at this valve, means everywhere this pressure will be transmitted. and delta P will be equal to F into A, because we are applying force F to the cross-sectional area A. If after applying the force on piston the pressure increases by delta P at A, then it will also increase by delta P at B and C and everywhere in the fluid and on the wall of the fluid of the flask, according to the principle of transmission of pressure. Pascal's law of transmission. Application of Pascal law of transmission. This law is used to make hydraulic lift. The situation is shown in the figure. Here two cylindrical body is filled with same liquid and they are connected with a cylindrical tube also, but both cylindrical tube have cross-sectional area different. This cylindrical tube have cross-sectional area A1 and this cylindrical tube has cross-sectional area A2. Now if we apply a force F1, this will generate a force delta P, and which will be transmitted all over the liquid, and so this will also transmit to this point. Using this principle, the hydraulic lift is acts. Let's see. If we apply a force F1 at area A1, then pressure transmitted will be P1 equals to F1 by A1, because we are applying a force F1 at area A1. So pressure here given is P1 equals to F1 by A1. Now this pressure will be transmitted to this area. Now if we consider here pressure is P2 and area is A2, then hence upward force resulted from this transmitted pressure in the second lift, F2 equals to P1 into A2. Because pressure will be same, so we have used formula F2 equals to P1 into A2. This implies F2 equals to F1 by A1, because P1 equals to F1 by A1 into A2. This implies F2 by F1 equals to A2 by A1, equation 1. Now if A2 is greater than A1, then A2 by A1 must be greater than equation 2. And from 1 we can also write from 1 and 2 F2 by F1 is greater than 1. This implies F2 is greater than F1. Thus we can lift a load after applying a smaller force. This principle is also used in hydraulic brakes. Let's consider, if we apply a small force, this will lift this lift, because F1, from this formula we see that F2 is greater than F1. If we apply a F1 and here F2 force is acting, but after solving this, see that F2 is greater than F1. So we here apply a small force. This will transmitted the force transmitted at this will be greater than F1. So this principle is used in hydraulic lift. Mechanical advantage, MA. The factor by which the applied force increases is called MA of this device. MA equals to F2 by F1 equals to A2 by A1. Hydrostatic paradox. Here three different sized tube is connected to each other, and these three vessel contains different amount of water or any liquid. Since now see, this is point P, this is point S, this is point Q, and this is point R. Because these 3 points are in same level from the free surface, so this must have same pressure. So we have, since pressure at P, Q and R have to be same, so the level of liquid in 3 vessels is same. but these three vessels contain different amounts of water. This is known as a hydrostatic paradox. That is PS equal to PQ equal to PR equals to H rho G. Thus we can say that with different amount pressure may be equal.